Good day to all those watching the video. This video is on countercurrent multiplication, the process by which the kidney forms a hyperosmotic medullary interstitium. This process is necessary for building a hyperosmotic medullary interstitium so that ADH can perform its function. ADH can reabsorb water in the presence of aquaporins. Aquaporin 2 on the apical side and aquaporin 3 and 4 on the basolateral side. The countercurrent multiplication function is performed by the loop of Henle. This is the loop of Henle and it has two main functional parts, that is a thin descending limb and a thick ascending limb. The thick ascending limb is thicker and the thin descending limb is thin. Here I am showing 300. 300 is the osmolarity of the fluid which is coming from the proximal tubule. It is isoosmotic, and this is a hypothetical model of how the kidney builds up a hyperosmotic medullary interstitium. So first we'll consider the thin descending limb. The thin descending limb is freely permeable to water. The thin descending limb is freely permeable to water. It has aquaporin 1 on both the apical and basolateral side, so it is like a fishnet. It freely allows water to pass through, but it does not allow solutes to pass through. The thick ascending limb is freely permeable to solutes. The thick ascending limb is freely permeable to solutes. It is a watertight compartment. It is not permeable to water. Hence, it is also known as a diluting segment. Of course, the early distal tubule is known as the cortical diluting segment. So the thin descending limb is freely permeable to water and impermeable to solutes, while the thick ascending limb is permeable to solutes but impermeable to water, and therefore it is also known as the diluting segment. It has the sodium potassium 2 chloride symporter on the apical side and a sodium potassium ATPase pump on the basolateral side. Sodium potassium 2 chloride NKCC2 symporter on the apical side and sodium potassium ATPase pump on the basolateral side. Please remember, the model of the countercurrent multiplication is a hypothetical model. Step 1 is flow of isoosmotic fluid. At the end of the proximal tubule, please recollect that the tubular fluid is isoosmotic. This isoosmotic fluid flows into the thin descending limb, then it goes into the loop of Henle, and then it travels into the thick ascending limb. So everywhere the osmolarity is 300 milliosmoles per kg. And as I cannot repeat enough, this is a hypothetical model. So step 1 is flow of isoosmotic fluid into the loop of Henle. Then we come to step 2. We have seen that the thin descending limb is freely permeable to water and impermeable to solutes, while the thick ascending limb is permeable to solutes. It is freely permeable to solutes. It has sodium potassium 2 chloride symporter on the apical side and sodium potassium ATPase pump on the basolateral side. And in the thick ascending limb, there is active transport of solutes out of the thick ascending limb. But its limit is only 200 because of back leak of solutes. So the 300 becomes 200, and in the medullary interstitium it becomes 400. And this is the main catch. This is the main catch. It is able to establish only a 200 milliosmoles per liter concentration gradient. Otherwise, you would wonder that by this one step only, it can create an osmolarity of 1200 milliosmoles per liter in the medullary interstitium. Why is it not able to create so? This is because in the lumen the osmolarity is 200, while in the interstitium it can become 400 only. The thick ascending limb has a ability to establish only a 200 milliosmoles per liter concentration gradient, a phenomenon known as single effect. It has the ability to establish a 200 milliosmoles per liter concentration gradient only. 200 milliosmoles per liter concentration gradient only. Now, step 3 is dealing with the thin descending limb. We come to step 3. In step 3, the thin descending limb does its function. So it equilibrates with the medullary interstitium. Please remember, it is like a fishnet with some charges so that water can easily pass through it. It has aquaporin 1 on both the apical and basolateral sides. Equilibrium between the descending thin limb and the medullary interstitium. So now the thin descending limb becomes 400, the medullary interstitium is 400, and the thick ascending limb, you guessed it right, it is 200 milliosmoles per liter concentration gradient. That is 200 milliosmoles per liter is the osmolarity in the thick ascending limb. Now we are moving more to the easy part. The first 3 steps, these are the 3 main steps. Now the fourth step. The fourth step is again flow of this fluid from the thin descending limb into the thick ascending limb. So it is able to establish a concentration gradient of 200 milliosmoles per liter, but now with this countercurrent multiplication, the 400 becomes 400 everywhere. 400 milliosmoles per liter in the thin descending limb, 400 milliosmoles per liter in the thick ascending limb, and 400 milliosmoles per liter in the medullary interstitium. So in the medullary interstitium, the osmolarity is 400. We can reach up to, the kidneys can reach up to 1200 milliosmoles per liter, but it cannot reach at one go because the thick ascending limb has a limitation. It is able to establish a concentration gradient of only 200 milliosmoles per liter. So there is flow of this isosmotic fluid from the hyperosmotic fluid from the thin descending limb into the thick ascending limb. And lo behold, we have completed the countercurrent multiplication. There is repetition of these steps 2 to 4 again and again and again and again and again. Repetition of steps 2 to 4 again and again and again, and that can lead to a urinary osmolarity of 1200 milliosmoles per liter. So you got it. Repetition of steps 2 to 4 creates a hyperosmotic medullary interstitium. So this is a hypothetical model. In step 1, there is flow of isoosmotic fluid from the proximal tubule into the loop of Henle. In step 2, there is active transport of solutes out of the thick ascending limb. In step 3, there is equilibrium between the descending thin limb and the medullary interstitium. And in step 4, flow into the thick ascending limb. This creates a hyperosmotic medullary interstitium, and the maximum it can reach is 1200 milliosmoles per liter. So that in the presence of aquaporins, particularly aquaporin 2 on the apical side and aquaporin 3 on the basolateral, 3 and 4 on the basolateral side, it can establish a concentration gradient, and ADH can facilitate the reabsorption of water. What is the maximum concentration it can reach? 1200. So the maximum concentration it can reach is 1200 milliosmoles per liter, and that is it. And this enables ADH to reabsorb water and form a concentrated urine. Thank you for watching my video and have a good day.